In this video, we're going to begin our discussion on Chapter 3. And like we've done at the start of each of our chapters, I want to take some time before we jump into the specifics of 3.1 to kind of give an overview about what Chapter 3 is all about and kind of where it maybe fits in the larger context of the things that we've done thus far. So really quickly here, I'm going to slide over to the side and take a look at the following. We saw that back in Chapter 1, our goal was to kind of welcome ourselves to the world of 3 space. We talked about things like points, distance, and vectors. We dealt with a lot of basic shapes, spheres, cylindrical surfaces, lines, planes, quadric surfaces. Again, the goal was to familiarize ourselves with this world and start to build some basic intuitions of how things function. In Chapter 2, we started taking a look at a specific kind of function, a vector function, these R of t's, specifically functions that had a single input variable, like t, but produced multiple outputs that we organized into a vector. The goal here again was to extend the idea of lines that we talked about back in Chapter 1 to the idea of a space curve. Not all curves that exist in space are straight lines, but some of them might actually be crazy, wacky curves that can go all over the place. Now in Chapter 3, we're interested in doing something similar to what we did in Chapter 2. When we talk here in this chapter about multivariable functions, functions that are not going to produce vectors, but instead appear to take in something like a vector. I'm going to be dealing with functions that have multiple inputs and yet only one single output. So you can see it's kind of like the reverse of what we did in the previous chapter. And the goal here is to really say, I want to extend the idea of planes that we talked about in that first chapter to now say, well, what would it be like if I instead had something like a surface, a landscape with rolling hills and valleys and all sorts of other things going on? What if it wasn't just flat? And so in this opening section, we're going to be doing, again, not really a lot of calculus, but more of just the algebra kind of going on with some of these basic multivariable functions that we can start to take a look at. So let's take a look over here and introduce our starting definition for the chapter. A function f of 2 variables is really going to be a rule that assigns every single ordered pair down in the xy plane in a specific set D to a unique real number denoted by f of xy. Essentially, if I think about this in terms of my x, y, z coordinate system, I'm going to imagine that for every single xy point that I can imagine selecting down here, that's going to correspond to some actual point up above on top of a landscape. Right? That when I plug in x comma y, my function can produce a corresponding value of a z. So D here is what I'm talking about as a domain. There might only be some x's and y's, x and y values that I can plug in, and the range would be the set of all possible values that f can take on. Okay. So familiar operations like addition can be used here. You can do all sorts of crazy things in terms of writing these functions. Notice here's an example of this kind of a function. I just say f of xy is equal to, well, take x and add the y. And I could wonder, what does this thing create? And what it will create is a landscape, but a landscape with what shape or what properties? Okay. Using our mapping notation that we talked about previously, remember that this just says f is the name of my function. And the first thing here is telling me the inputs. This is saying I'm getting 2 inputs from the real numbers, and that those are getting mapped to, they're getting turned into a single real number at the end. So let's go ahead and just take a look at some basic introductory examples here, as this idea is actually fairly simple. In fact, I think it's more intuitive than the ideas of vector functions. Take a look here, example number 1. Suppose I have this landscape out in space, this multivariable function. Now, I don't know what this landscape looks like, and it's not your job to know that either at this moment in time. But can I go ahead and try to just understand how this function works? Can I do simple things like find the value of f of 2, 1? Well, sure, if I want to calculate f of 2, 1, it's probably no surprise that the x is represented, or the 2 is representing x, the 1 is representing y, so all I do is go to my formula and I plug in 2 for x and 1 for y. Okay, if I do this, of course, I'm going to get square root of 4 up top over 1 on bottom, and so I get a 2. That 2 represents a z-coordinate, right? So I plug in an xy, and what I calculate back out is a z. But of course, I could also recognize that there are going to be then possibly some values for either x or for y or for both that I shouldn't really ever plug into a formula like this because it would cause a mathematical error. Something right away that would probably pop out to you is like, I can't pick a point over here where the x coordinate is a 1 because that would automatically force me to divide by 0, and I can't do that. So when I write out the domain, my set of possible x comma y values that can work, and I want to put that in set notation, I can start kind of by doing the following. First, I can just note to myself some of the things that I can see need to be true. I know that x cannot be the number 1. And I could also see here that whatever I have underneath that radical would automatically have to be something 0 or bigger. I can't get a negative under there, and so certain combinations of x's and y's might make that happen. I want to make sure I avoid those. To specifically write this in set notation, I would say my domain, remember, is a collection of a bunch of things. So on the left side of this vertical bar are the things I'm collecting. Here I'm collecting ordered pairs, x comma y's. And on the right side of the bar are all the restrictions on what those things can be. And so actually I can just kind of copy down exactly what I had written up above. I need these two properties to be true in order to say that my x comma y pair is a part of my domain, that it's an allowable value. But of course you might then ask the question, okay, Kyle, but so is there any way for me to tell then or to know what all the possible values of x comma y would be? What are all the possible ordered pairs in the xy plane that would work? And it is possible to do this by sketching a picture of my domain. To do this, I'm going to just go ahead and sketch out a big set of axes. I only need the xy plane here because I'm only interested in the input values. So on this plane, what I'm going to do is kind of mark off any value that is off limits with red. And so one of the things I note right away is, well, I know that x cannot be the number 1. So that means that literally any point in existence along this line where x is always a 1 is bad. I can't use 1 comma 6 or 1 comma 0 or 1 comma negative pi, 1 comma a million. They're all bad. But what I can do is use points as long as they satisfy this other condition. Well, note if I was to take this other condition and think about rewriting it a bit, I could actually state that this is the same thing as y being greater than or equal to negative x minus 1. I'm just sliding that x and that negative 1 to the other side. And if I also kind of think about this as y equaling negative x minus 1, I could easily go ahead and start to create the picture of a line here down in the xy plane. It would be a line with a y-intercept of negative 1 and a slope of negative 1. And so I think it would be a line that goes through these 2 points here, and I'll continue to sketch the rest of it out. I'm sketching this in green because I know that if this property is true, if I'm equal to this value, right? If y is equal to the negative x minus 1, that's okay. Any point on the green line is fine. But also, I'm okay as long as the y value is bigger than what's on the line. So I'm thinking about this inequality. Since y is larger or equal to the line, I would also be okay with literally any other point that exists up here. So this is my universe of all points that exist that are good. And of course, then that means all points that are not green are red. So I can kind of maybe quickly see here, is 0, 17 going to be okay? Yeah, it's going to land in the green. What about -2, -5? No, that's going to be bad, right? And I can kind of do that just based off the picture. The green is all the points that are good, and the red is all the points that are bad. If I ever ask you to sketch the domain, I'm going to be primarily interested you highlighting for me, what the green points are, not necessarily those red values. Although typically I will still include values like here at negative or at +1 to indicate that those values are not included because I'm kind of starting to shade over them. Hopefully this makes it feel, at least initially, that like a lot of what we're going to do with these functions in terms of like plugging stuff in, figuring out their inputs and outputs is relatively simple. And we'll take a look at another example kind of similar to this with inputs and outputs in the next example.